Hi, I'm Tammy Lassiter-Clare from Portland State University. I'd like to tell you about XRF spectroscopy. I'm dividing the topic into 3 sections. In this first mini lecture, I'll describe what type of information you can learn from XRF and why do spectra appear as they do. By the end of this mini lecture, you'll be able to do basic peak assignments, which is the first step in interpreting an XRF spectrum. X-ray fluorescence spectroscopy, or XRF, is a non-destructive and ambient technique. Non-destructive means that the sample itself is not consumed during analysis. Ambient means that the analysis is done in the regular environment, as opposed to some techniques which require that the sample be analyzed under vacuum conditions. XRF is primarily used to identify which elements are present in samples. Some elements cannot be easily detected because ambient air absorbs their energies. Those elements are circled in red. As you can see, the elements that cannot be detected are organic elements, including carbon, oxygen, and hydrogen. Elements that can be detected by X-ray fluorescence under the right instrumental settings are circled in turquoise. So XRF is very useful to detect the presence of metals. Quantification of elements by X-ray fluorescence is pretty tricky due to matrix effects and interatomic absorption, which we won't go into. But it is fairly straightforward to determine the relative amounts, such as does this sample contain more iron than this sample does, using X-ray fluorescence spectroscopy. Here are images of 2 different XRF instruments. On the left is a handheld instrument. It can collect elemental information over an area that is roughly the size of a tic-tac. On the right is a scanning X-ray fluorescence instrument. The spot size of that instrument is much smaller, roughly 1 millimeter by 1 millimeter. And that instrument is motorized, allowing it to scan across a larger area, collecting elemental information from different points. Software can construct a map showing how the abundance of each element changes over the mapped area. When using a scanning X-ray fluorescence instrument, the instrument itself is motorized, allowing it to line raster, line by line across an area, collecting elemental information at each step along that line. Software can construct a heat map showing the abundance of each element as it changes over the mapped area. The detail of an 18th century Japanese woodblock print by Suzuki Harunobu is shown in the middle. To the right is an XRF map for iron. That map was produced from a series of individual spectra shown in the lower left. You can see that as the sample moved from points 1 to point 5, the intensity of the iron peak decreased. To produce the false color heat map, more than 1,000 spectra were collected across an area of approximately 1.5 by 1.5 centimeters. The instrument was set up to collect data for 10 seconds per point, and it takes the instrument roughly 10 seconds to move over to the next point. So to collect the data for the map shown, it took this instrument about 5.5 hours. X-ray fluorescence instruments emit X-rays that are directed toward a sample. Because X-rays are being emitted, radiation safety is required to use an XRF instrument. This figure shows what happens to an atom when it is struck by an X-ray. First, an X-ray ionizes a core-level electron in the atom. The electron absorbs the X-ray energy, causing it to fly out from the atom, leaving a vacant spot in that orbital. An electron occupying a higher energy orbital relaxes to fill the vacancy left by the ejected electron. Because that second electron has more energy than needed to occupy the vacant orbital, the second electron must give off that excess energy to occupy the lower orbital. The excess energy given off by the second electron is called a secondary X-ray because it was emitted by the second electron, and because its energy is within the X-ray region of the electromagnetic spectrum, hence secondary X-ray. That secondary X-ray is then detected by the instrument. Let's compare two different elements, A and B, and see how their secondary electron energies differ. These two figures show possible X-ray emission lines or energies that can emit when vacancies are created in different orbitals within each atom. K lines result when a vacancy is created in the K orbital. L lines result when a vacancy is created in the L orbital. M lines result when a vacancy is created in the M orbital. Depending on which electron fills the vacancy, the subscripts alpha, beta, and gamma are used to differentiate the different energies. For element A, we can see that the K lines are taller, meaning that they are more energetic than the corresponding K lines for element B. Notice the left panel for each element shows the K lines in an energy level diagram. The detector inside the X-ray fluorescence instrument is able to measure the different emission energies of the atoms as they emit X-rays. Software connected to the instrument converts the energy of each emission into a spectrum. The corresponding XRF spectrum for element A and B is shown in the lower right panels. Notice that energy is now plotted on the x-axis, which is as if the left panel were rotated. Observe how the length of each line matches up in the left and the right panel. Let's spend a bit more time understanding an XRF spectrum using a copper-nickel alloy as our sample. Shown in the energy level diagram in the top left are the K alpha and K beta lines for copper and nickel. Notice that each line is a different length, which you now know means that their energies are different. In the right is an actual XRF spectrum for a copper-nickel alloy. Notice that nickel K alpha peak is the lowest in energy, and the copper K beta peak is the highest energy. What we are seeing in the spectrum is the result of many thousands of X-ray photons ejecting one electron from each of many thousands of atoms. Once an electron has been ejected from an atom, which a secondary electron relaxes to fill it, whether it is from an L or an M orbital determines the energy of the emitted secondary X-ray. So another way to think of that is to understand that each peak in the spectrum was built up from many thousands of secondary X-rays. By filling each peak, I hope to show you that each peak results from the accumulated detection of the many thousands of emitted X-ray photons from thousands of separate atoms. You may be wondering why the heights or the intensity of each peak is not the same. Notice that the K alpha peaks are taller than the K beta peaks. The relative height of copper's K alpha to K beta peak correlates to the probability that an electron will relax from the L or M orbital to fill the vacancy. What the spectra show is that it is more probable for K alpha emission to occur than for K beta emission. Or, in other words, it is more likely for an L electron to fill a vacancy in the K orbital than it is for an M electron to do so. And for any given pure element, the ratio of K alpha peak height to K beta peak height is a constant value for that element. To summarize, not only can elements be distinguished from each other based on their emission energies, each element also has its own characteristic peak height ratios. Shown in this figure are 8 separate XRF spectra. They are displayed in what is called a stack plot. Each spectrum has been shifted upward so that they do not appear vertically on top of each other. Notice too that the axes are clearly labeled with titles and units. This is a clear way of displaying the data. You are now ready to try out identifying elements based on their position in an XRF spectrum. The 8 vertical turquoise lines are markers to show you which peaks you need to assign. The partially blank table lists the energies of those 8 peaks. Refer to a table of X-ray emission lines, which has been provided in a separate PDF document, to determine the element name, symbol, and emission line for each of the 8 peaks. As you work, do you notice any trends? Are there any ambiguous assignments? In the next mini lectures, I will elaborate on XRF spectral interpretation. For now, just do your best and try it out. See you next time.